welcome everybody to another one of our TFTC webinars. This is a special webinar uh, which is taking place on Wednesdays, where we usually have our webinars on Fridays at 11 a.m. But it's a special webinar. We have a special guest from China, Dr. Kan Wu. He'll talk about a challenge, one of the challenges of the KDD 2021 KDD Cup, which is called City Brain Challenge. How many vehicles can you serve at most with a city scale road network? He'll discuss this challenge, and also he'll talk about a simulation platform that's recently developed by them, I think. And Khan, he's a postdoc researcher in the Research Center for Intelligent Network at Zhejiang lab. And I don't know whether I pronounced that right.
Yeah, you are right.
Okay, cool. So he did his bachelor's and master's in Arizona State University, and he got his PhD in civil engineering from the Penn State. His research interests are in public transportation, traffic operations, and traffic control. So, Khan, the floor is yours. Thank you again, and we are ready to hear you.
All right, thanks, Rafi. I appreciate the introduction. Today, I will talk about the KDD Cup 2021 KDD Cup. How many vehicles can you serve at most with a city-scale road network? So, this is actually a dissimulation of a competition rather than a formal research work presentation. I really appreciate everyone for taking the time to join, and I hope you enjoy the presentation. So I will go through the slides first and leave some tough questions for my friends to and Hua to answer maybe. So before I start, I just want to give you an overview of today's presentation. Firstly, I will give you some backgrounds on the KDD Cup, and then I will introduce the competition and probably some benchmark solutions for this competition you might be interested. And then I will show you how to get started for the competition, like if you want to join. And I will go through the slides as quick as I can, and so we can leave more time for the question and Q&A. So the KDD Cup is a most prestigious data science competition that's been run by SIG, the Special Interested Group on Knowledge Discovery and Data Mining, since 1997. It's like has been like being had for over 2 decades, I guess. And look at those numbers, like in KDD Cup the 2019 only, like if it had more than 2008 registered teams from over 39 countries and 230 institutions. So it is a very popular competition. And recently, like the transportation related problems are being more popular to the KDD Cup organizers. Like for example, there are transportation related competitions in KDD Cup 2017 and 2020. And this year we are hosting the City Brain Challenge, like aiming for an efficient traffic coordination strategy to serve more vehicles. Basically, it's like a competition to solve some real traffic congestion problem. And before we hosting this competition, we actually did a simple survey. Like look at those two numbers from the two largest cities in the world, Tokyo and New York City. We can see that as for the number of registered vehicles, there are 43 more registered vehicles for Tokyo than New York City. But if you're looking at the road network size and the number of traffic signals, those numbers are not like as huge difference as the number of registered vehicles. So here comes the question to us, like, why? It looks like Tokyo operates its transportation network more efficiently, but why? And the further question being that how many vehicles can be served with a city-scale road network, and of course we need to maintain an accepted delay or level of service. We might already know that the road network size, the traffic demand patterns, and the traffic management strategy are main factors that affect the answer. And we know that the road network size and traffic demands are hard to change. But the traffic management policy can always be optimized. So that's why we are hosting the City Brain Challenge. So the scenario here is that we will provide the participants with a city-scale road network, and I mean a city-scale road network. I mean that there are like more than 1,000 intersections, not 100, not tens intersections, like more than 1,000 intersections, and the traffic signal timing can be optimized. The objective is maximize the total number of vehicles served via optimizing traffic signal setting. In particular, for each intersection, we need to develop a model to intelligently select a signal phase to be actuated for each time step. And I think since this is a traffic transportation committee, I would just assume that you guys already know the traffic signal setting. Like for a four-leg signalized intersection, there are a total of 8 types signal phases. So the problem is that given the road network and given the sample OD demand and fixed route, the participants need to develop a model to maximize the cumulative number of vehicles served. That is the problem setting, and we also evaluate, once you submit the solutions, we also evaluate the solutions for based on the 2 evaluation metrics. The first one is, like I mentioned before, the cumulative number of vehicles served. This includes the vehicles that are still in the network and the vehicles that have already left the network. And the second evaluation matrix is the delay index. So the delay index is defined. I also put the equation here, but I just want to make a quick introduction. This is quite straightforward. Like for a trip, the delay is computed as actual travel time divided by if it's free flow speed. And for those uncompleted trips, the rest of trip travel time is just estimated using free flow speed. And we use the equation as I put here. For all the vehicles served, like we have an average delay index computed over all the vehicles served. And for the for scoring each submission, we will keep monitoring the delay index computed over all vehicles, like all the vehicles. And once the delay index reaches the predefined threshold, say at the 2.0, and apparently the delay index is greater than 1, so we will set a predefined threshold. Once it reaches the threshold, the test process will be terminated, and the solution is scored as the cumulative number of vehicles served. And also for the first or the warm-up round, which has already started in April 1st, we did not set the delay index, just because this round is just for those participants to get familiar with this problem setting. And for more details about the evaluation matrix, you can always click the link I put here. And there are a total of 3 competition phases. The first one is warm-up. It's already started at April 1st, and participants will just practice with the original road network. I think it's about 20 signalized intersections with light traffic. Just get familiar with the problem setting and the simulation environment. And here's an important date I just want to mention. So all participants or team members need to sign up by April 30, the end of April 30. This is an important date because if otherwise you will not be able to take part in this competition. So the second phase, or the qualification phase, starts at May 1st. It ends at it will last for a month. And in this stage, we actually increase the size of road network. So it's about 1,000 intersections, and each team will be provided with the test traffic. I mean, the test traffic for the test traffic. I mean, it is just the traffic data we used for scoring your solution. So and besides this, the task traffic data, we also encourage you to create your own data set for training if you use data-driven method, say if you use a reinforcement learning method. That's for the qualification phase. And the final phase would be start at June 1st. And for this phase, like, we will invite the top ranked teams from qualification phase. And we will provide the computing platform, so our teams will just submit their code and run their solutions, including training and testing those models in our cloud computing platform. Again, the road network size would be more about 1,000 intersections. But different from the qualification phase, we will provide just the sample traffic data, but it is not guaranteed that the data for scoring the solution are the same as the sample traffic data. They might be different. So the reason why we're doing this, because we wish to find a solution that adapts to changes in demands of OD pairs. That's a common case, like in real life, because traffic always changes. Despite with some similar patterns, it always changes. So that's pretty much the whole phases, the whole computation phase. And again, I just want to mention again, because this is very important. All participants need to sign up by the end of April to make sure that it's being clear. Okay, so to facilitate this competition, we also opened the CityBrain Open Research Platform, the CB Engine, for the first time. This one is a very high efficiency engine. It supports experience with more than 1,000 sections and more than 100,000 vehicles running simultaneously. So we use some parallel computing techniques to ensure this high efficiency, and also a cloud computing cluster with 100 multi-core machines will be also provided for the final phase. And it also includes a microscopic traffic simulation environment, and for for the traffic models, we also consider that we need to mitigate the impact of randomness. For randomness, I mean that we want to make sure that if your solution is score higher, it is just because you do a good job on traffic signal timing, not not because of the intelligent route chosen by the vehicles. So we use the fixed route setting. And for curve following models and land changing models, we just use a simplified model, safety distance curve following models. And for land changing models, again, like to minimize the randomness, so we just allowed the mandatory land change. Like the land change is just for what, like for example, a vehicle enter a road segment at the entrance. If it is expected to make a left turn, it just enter the left turn lane, and we would not make any change in the middle of lane. So again, just we just want to minimize randomness, and also we set a safety distance. We use a safety distance gap acceptance model. So this is pretty much the CB engine, and actually this is the first time we open like this engine open to the public, and we as you can see, like the traffic model might not be optimal, but we will keep optimizing the models after the competition. And this engine, like for now, it just support for this competition, and we are considering to open it to public in the long term. So to better explain this computation, I will just quickly go through some benchmark solutions that we used. And again, as you can see, there are basically there are two families of models, methods, like the rule-based methods. This one, as a transportation engineering researcher, I would say I'm more familiar with this family, like fixed time, green wave, max pressure, and the recently measured like parameter metering control. And another family would be reinforcement learning based methods. So I just go quickly through those benchmark solutions. If you want to know more, you can always refer to the link I put here. So for rule-based method, we already implement this fixed time method. We might already familiar with this one, as a transportation researcher. So we select the signal phase setting, cycle length, phase split, based on traffic volume analysis. This is quite a simple one, but I would say it is a good benchmark solution. And for max pressure, we define the traffic pressure as the difference in upstream and downstream queue length, and each time the decentralized traffic controller just select the just make a greedy select, which means that just select the phase with max pressure to actuate. Like for this example, in case A, phase 2 is actuated. And for reinforcement learning, actually a reinforcement learning agent learns about the sequence of decision to inform future decisions. And we have an agent and an environment. Basically, the agent just receive some information from the environment. We call it state. Apparently, the state is not represent everything. It's just a subset of the reality. And for the environment here, in this particular case, we just provide it just means the simulated environment. And the agent keep interacting with the environment. It will get cumulative rewards each action it take. So the goal is maximize the cumulative reward. And in reinforcement learning, a common used method is we use a discount. We will discount the future reward. It is obviously that the immediate reward is more important than the future ones. So the goal again is to maximize the cumulative reward. And this is pretty much some background. Again, I'm not quite familiar with reinforcement learning. I just want to try my best to explain this method. And in this problem, we can use like the state as, for example, the queue length, the volume, delay, speed, and phase duration and position of vehicles. And the reward might be defined based on queue length, the waiting time, change of delay, and so on. So the action is apparently the signal phase actuation. Like at each time step, we select a phase, the signal phase. And this is pretty much the reinforcement learning based method. I will further talk about, like, if you join this competition, how do you set up the environment, like what's the code structure, and how to visualize the results, and some demos of benchmark solutions. The first step, you need to download the Docker image and start a kit in order to like set up your environment. And you can the second step, you can run test file in the Docker. I will not like talk about too much. I will not talk about the details, but you can always check the tutorial link as I put here. And again, this is the code structure. We have, like, you need to implement the agent py file, and to submit your results, you need to update those two files. And to evaluate and score your results, you need to change the evaluate py file. And we also have a simple demo here, and the other files, including the data we provided and the log. By log, I mean the immediate results and the final output file. And again, the tutorial output here. And here's one interesting thing. Like we did actually provide a visualization method approach for your results. Like in order to visualize your results, you need first install the yarn, and you need to apply a Mapbox token via creating your Mapbox account. And here's I put the step-by-step for visualizing your results. And this one is actually I received from one of the participants. He just said the visualizing is quite good. So I just want to show you here. And this one might not be too much details. This is just a demo of fixed time implementation. So for this one, all traffic signal phases are pre-timed, and traffic signal phase will be selected sequentially in a predefined order. And as you can see from the code, we observed the current time step, and we set the signal phase. This is quite a simple one, and just for benchmark solution. And this one is a demo for DQN implementation. This is actually come from a conference paper we previously submitted, the pressure light. And for this one, we define the state as number of vehicles by lane, and the reward is the traffic pressure. Again, the pressure is defined as the queue length difference between the upstream and downstream lane of a intersection. And that is pretty much about the how do you get started, and the timeline I also put here, like again the important dates and warm up, qualification, and the final. And also please be notified that all deadlines are on the 23:59 p.m. anywhere on Earth. So that's pretty much how what I will present, and I will leave some time for questions.
Thank you, Khan, for your presentation and this interesting challenge. So now we are open for questions. If you have any questions, you can unmute yourself and ask your questions, or you can type in your question in the chat section and I can ask you.
I have a few questions. And again, thank you, Khan, for this informative presentation. And thank you, my former student, Tu Su, for putting this together. So the network that we'll be using, is it of a real city? And also, do you have more details about it? Can we, for example, will we have access to the length of the streets, stuff like that?
Yeah, I can give you some details on this. The first question, is it a real city? Yes, it is. It's a city in middle of China. So it's a city like with, I think it's about 3,000 intersections, the road network size. Yeah, about 3,000 intersections. And the second question.
Can you disclose the name of the city, or that's not going to be?
Yes, it's Nanchang in China. I can.
Okay.
Yeah, if you apparently if you know Chinese, you can always say.
Yeah.
Okay. Here. Yeah.
I lost my student. He probably knows, right? How?
Yes.
Okay.
I think so.
And so it has bridges, or the network is going to be on. Is the picture we're looking at is that the network?
Yes.
Okay. So it has bridges.
Yes, it has like 3 or 4 big bridges. Yes.
And it's going to be mostly the whole city, or a portion of this?
I would say the most dense part of the city.
Okay.
Like, with most population. Yeah.
Okay, great. That's very useful. Yeah.
And about your second question, like you ask, can we access to further information about the length of the road? I would say yes. You can go. Let me see. Let me just quick show you. All right. Like if you go with this tutorial, it will show you how to access the information you might need, like the speed, the number of vehicles, the road names, like any information. Okay. I would say I would say any information that to facilitate your model method.
Okay. Great. Now, any more details on this car following model? Or mostly the car following model. Is it a standard one, or can you comment on the origin of that model, etc.?
It's not it's a simple one, but I would say it very close to the cross model. Like we just assume that like those vehicles just make a conservative operation. Like it always assumes that the leading vehicle would be decelerate at its maximum acceleration rate. So again, it's just to ensure that the vehicles will not be crashed. Like,
so Dr. About
no. Yeah, actually, Tu is just trying to answer your question.
Oh.
Can you hear him?
I can't hear him.
You can't hear him? He said this model is very close to the default one in Sumo.
Oh, okay.
Yes. But again, as I mentioned before, I would say this is not an optimal model. We will keep updating. Like make it as better as possible. But for now, this model is just a simplified one because
Right.
for the computation, yeah, for the computation we will stick to these models, simple models.
Do you know if they have realistic acceleration?
Realistic.
Acceleration?
I think the acceleration, the maximum acceleration is like 2.5.
Okay, so it's bounded by the acceleration. Okay.
Yeah, the predefined acceleration.
Very good. Excellent. Sounds exciting. Any more questions from the audience?
Yes, Dr. Wu, thank you for the information. Can you hear me?
Yes.
Okay.
We can hear you.
I have a couple of questions. First is a technical question. So I try to play with Docker in the simulation. I'm wondering, have you tried the code in one of the slides to show installed it from Docker and run it? It looks like it should be run on a Linux machine.
Yes.
I tried it. To be honest, it didn't work for me. So I'm guessing if you or the committee can provide more tutorials on setting up the environment. And I also guess many of us are not using Linux, maybe Windows probably. So is there a recommended way to run the simulation and develop our own algorithms in Windows platform? Can you answer that question?
Yes,
please?
This is actually a good question. Actually, for the first time, I'm trying to use a Windows machine, but it's very complicated. You need to set up the Docker for Windows. Like it's very complicated thing. So then I let one of my members just use the Ubuntu, like the Linux. It works fine.
Yeah.
But for any question you I can for any question you can raise an issue on the GitHub, or if you we can connect to each other for
Yes.
I will try to answer this question.
For this question, I suggest that maybe we can have the YouTube video, a simple one, to show how to set up the environment in Ubuntu or Linux. I think that will help us a lot. Otherwise, we need to spend a lot of time figuring out how to use Docker.
Well, I think under Windows it is usable because if you have set up your Docker, then it is usable. And I think on the website of the installation, they have one comment on how to set up on Windows. Let me send the link here.
Yeah, I think why you can share your window if you.
Yeah, I can share my window. So I don't know what kind of. You guys see my window?
Yeah, I can see.
Yeah, so I think on the starter kit GitHub page, they had one comment saying that if you are I think most of the questions for people who are using Windows, they come into this error, and they said if you are operating on Windows, you found this error, then you should set this. Then I guess this should be workable under Windows, and all you need to do is to set up your Docker. So maybe you could have you already set up your Docker on Windows? Is Docker workable?
Hey Hua, actually I'm using Ubuntu, so I was stuck to find the path of the city challenge. And can we go back to that slide or the tutorial page? So I think the second line, it says we need to go to the path when we pulled the Docker container, but I could not find that.
Oh, I see. So you're saying that
locally. Yeah.
the tutorials are there's a Docker pull, something like that. It is the Linux
Yeah. Yeah, after that
command,
line,
right?
we can pull, yeah. But after we pulled that Docker, how to find the find it locally and run it, I was
Oh,
stuck
okay.
there. Yeah.
Okay. I got your question. And maybe like maybe I'll talk to the the technical
Yeah.
part
Yeah.
students, and they could like update something here or update
Yeah.
the starter kit document.
Yeah. I'm
Yeah.
suggesting if it would be great if we can have a video. It could be very short, but it can help. Yeah.
Yeah.
Thank you.
Yeah. Yes, that's a very good question.
Dr. Kane, I have another question on the final. In the final round, you said you will try diverse traffic demand to test our algorithm. I'm wondering, can you provide more details, or is it allowed to do so now? I'm wondering how different the final traffic demand would be from the test data, like in the qualification round. You say you will use test traffic, and I'm assuming it's the real traffic data. And in the final, you say you will test the algorithm, whether it can handle diverse unknown traffic flows. So for that diverse unknown traffic flows, what it would be?
So we will provide the pattern of the traffic flow. Like for example, like there are congested origins like at some locations, but we will not provide the actual traffic demand there. We just provide some informative information, but we will not provide the actual data. That is a unknown diverse traffic.
So I'm assuming it will be quite random.
Not too much random, but just with some variance, like variance from the sample traffic data.
Ah, I see. Okay.
Yeah, not random. Mm-hmm.
Yeah. What about the final congestion level? Is it based on the peak hour data, or you will have your own?
It will be derived from the peak hour data, but will apparently the simulated environment is different than the reality, different from the reality. So we will do some data augmentation for sure. Yeah.
Okay, I see.
Mm-hmm.
Final testing. Yeah. I'm curious about some behaviors of the simulation, especially when vehicles are near or at the intersection. So, because you mentioned the vehicles will have fixed routes, so I'm wondering, will vehicles wait and block the lane forever if it does not get to green to go? Or it will be teleported like Sumo or Vism is doing for intersections. And will vehicles come into the intersection and block the box, maybe? Do you have any details about that?
I'm sorry, you said.
Yeah. I know for many traffic simulators at the intersections, some behaviors of vehicles will become strange or weird. For example, some vehicles might enter the intersection box, but due to the downstream queue, it cannot be cleared. And for many traffic simulators, the simulator will remove those vehicles automatically. Yeah, I'm wondering for the simulator, what will the simulator do for those vehicles that are waiting too long at the intersections?
So you are asking about the intersection, the behavior at intersection box,
Yeah.
right?
Yes.
And the answer would be that if the downstream is blocked, the vehicle will never enter the intersection box, like the box room you mentioned. It just wait at the upstream lane, even though it's green. Even though it is green. So again, we just ensure that, yeah.
So there's not going to be rerouting?
Oh, sorry.
There's no rerouting then? If the downstream link is jammed, it'll wait there forever?
I think no.
No. Fixed route. The route is not.
Yeah.
There's no resorting.
That can be a problem because the network will tend to have bifurcations, which means that once that happens, then congestion will spread probably throughout the whole network, and there will be gridlock effectively. We're finding that that's the most important factor actually of traffic control, is the way people react to downstream blockages. So if you're not gonna do anything with that, I'm fearful that the simulations will collapse very quickly.
Yes, that might be a problem.
But unless the demand level is not too high, right? If you keep it at, free flow or capacity a little bit, maybe it's not a problem. But once you get more congestion, and that's a typical problem we face all the time in using existing simulation packages, right? And they have resorted to things like teleporting that Hao was mentioning, right? That it's very unrealistic, of course. But it goes to say that the impact of behavior at intersections is really important for these networks.
Yeah, I think so. But like if you make, I don't know if I'm right. I'm thinking right. If you made a gridlock, let's say gridlock, your solution might be not a good solution, I would say. Not as better as other one that would not cause gridlock.
It will be terrible because travel times will go to infinity, right? People are not moving. Yeah.
Yes, and then your solution would not rank high. Like you might not able to enter the final phase. But again, I would say that your recommendation is very useful. Like we will carefully to set the traffic demand, like not too high, to make a gridlock for all the solutions. I would say if all the solutions there are gridlocks, then the traffic demand would be too high for this competition.
Yeah.
Yes.
Very good. All right. Any more comments, questions from the audience? All right. Hearing none. So again, let me please thank the speaker, and again, Tusu for setting this interesting informational session. We look forward to the competition.
All right. Thank you, Lava, Dr. Lava. Thank you.
All right. And I believe we're going to share your presentation. There's many useful links, as somebody mentioned, so keep an eye on that. We're going to post it on the group chat, right, Rafa?
Yes.
It's shared it.
Google Group. All right.
Link to the video recording.
Excellent. All right. So everyone have a great rest of the day. Good night to the people in China, and thanks again for this interesting presentation.
Thank you.
Thank you, Khan.
Thank you.
Thank you.